It is my privilege to introduce Mike Schiffman, a former coworker and someone who has considerable prowess with many things, including a very deep understanding of TCP/IP, but I'm going to let him point you towards his previous work that he may wish to address. He's Director of Security Architecture for At Stake and is going to talk to us about his 802.11 toolkit. So without further ado, Mike.
Hey. Oh, okay. Thanks, Ray. Is that too loud, or is that all right? Seems awfully piercing way over here. All right. So, you know what? All right. As Ray said, I'm going to be talking about a wireless toolkit today, and on a broader scale, why we need a wireless toolkit. Before I kick things off, I did want to mention that when I went to get my badge this morning, turns out that I had already registered. Somebody said they already registered and got my badge. So if you see a rambunctious little scamp running around with a Mike Schiffman badge that isn't me, tackle him or knock him out, whatever it takes. Because I guess they don't check IDs over there when they get badges out. So just as an FYI, it's a computer security conference. Anyway. So today we're going to be talking about, obviously, the need for this 802.11 toolkit. The presentation is a little bit code-rich at the end, so if you're not a programmer, I apologize for that, but you know, I had to do something to fill up the time. So there's going to be a lot of talk about code. Of course, we're going to start off with an introduction, myself, an overview of the presentation. We're going to dip into a protocol primer. I know Bruce gave a brief primer in the last presentation. There's a small amount of overlap, but not too much. So, am I doing something wrong here? Huh? Oh, is that what I do when that happens? I don't know. All right, Ray's on the case. From there, we're going to talk briefly about some protocol flaws and where 802.11 is deficient. We're not going to talk too much about the problems with WEP. You want to make sure these guys are off? Then we'll look at some existing network 802.11 security tools, and we'll find out where they come up lacking. Then we're going to segue into Radiate, which is the 802. I don't know, can you turn the mic down a little bit? That might help, because I talk kind of loud sometimes. It's like the DJ back there. Can you turn my levels down? No? All right. And after we talk about Radiate, which is the wireless toolkit, we're going to learn how to integrate that with Libnet, which is a library for building packets on a traditional wired network, and how we can use both tools together, toolkits together rather, to build 802.11 security tools. And we're actually going to run through a tool at the end of this presentation, some source code. And I'll close with comments, questions about anything really. We may run short, we may not, we'll just have to see how it goes. So a brief introduction who I am. I'm a senior consultant with At Stake. As I'm told, the premier provider of digital security services. We are, actually, it is true. I work with some of the best and brightest people in the industry. I'm constantly amazed with working with guys like Tim Newsham and whatnot. I also sit on the technical advisory board for a company called Qualys. I'm consulting editor for Wiley & Sons for their open source book line. Oh, that's good. Thank you. I traditionally have more of an R&D background, not really a classically trained R&D background, but more of a sort of ad hoc one. Some of the tools and things that I've done that you may or may not be familiar with. I wrote a tool called Firewalk with a colleague of mine, David Goldsmith, a few years back. I actually presented on that at Black Hat 3. Libnet, which most people who are familiar with me are familiar with that, I suppose. We'll talk about that. I'm sorry? Oh. We'll talk about that a little bit later. Another library that was just released actually last night or 2 nights ago was libsf. It's a stack fingerprinting library, exports Nmap-like functionality into an API that you can use in your own tools. Libradiate, which we're going to be talking about today, and then I used to do Frac Magazine for a while. And those are some of the books that I've written and currently working on. So what you're going to learn today, we're going to do a brief intro of the 802.11 protocol. I apologize if most of you guys know this stuff. Most of you probably will, some of you might not. In any event, we're going to sort of power through that stuff. We're going to talk about some of the weaknesses in 802.11. Again, you might know that stuff as well, but this is just sort of building the foundation. Then we're going to learn how to use Libradiate to build custom 802.11 security tools. And also, you might learn, if you pay a lot of good attention, you might learn something about yourself. That's for Nate. What you should know, you should have a general understanding of the TCP/IP protocol suite, primarily layers 2 and 3 today. A general understanding of wireless, which I'm sure everybody here has. General network security concepts is always helpful, and the C programming language is going to be sort of useful to know towards the end of the presentation. Before I delve too deeply into these things, I kind of want to define two things: a network security tool, or tool, which we'll probably use interchangeably throughout this presentation, and a toolkit. And the first definition, I'm not even going to recite it, you can read it. By the way, I should note, the presentation you have in front of you is slightly different from the one up here. This is the polished, super new, 0-day one, and the one in the book is a little bit older. But that just makes you want to pay attention more. So network security tool is blah, 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 right? You see the definition up there. It's pretty dry, but for our purposes, it's going to be effective. Test the security of across a communications medium of a host, a system, an entity, what have you. A toolkit, as far as I'm defining it, is an API or set of APIs used to build a network security tool. And as far as we're concerned today, that's going to be a C programming library. And as sort of an aside, some of the nomenclature that I've defined in a model that I've come up with for network security tools, which I'll briefly mention at the end of the presentation. These APIs are also components in building techniques which you use to build network security tools. So I'm going to kind of go through this stuff relatively quickly because obviously you wouldn't be here if you didn't know this stuff, and the presentation before me sort of covered a little bit of it. 802.11 is everywhere. We all know that. It's in this room right now, and as I understand it, in several of the rooms on 4 different channels, which I'm going to probably be doing a live demo later, and that might complicate matters, but we'll get to that. So 802.11 networks are fabulous inventions. They're used across the board, corporate America, but you also see them in coffee shops and hotels and airports, and you got your neighbors setting up residential ISPs, so they can, you provide you with free or cheap internet access while proxying all your communications and stealing all your email and what have you. Many new products and services on top of 802.11. Sure, newer, faster physical interfaces are being turned out on top of on top of the same layer 2 protocols. By the way, this is a perfect time to mention that if I go too fast or if I mumble something, feel free to interrupt me and ask a question. I have no problem with that. If I want to take the question offline, we'll just talk about it afterwards. So obviously there are a few security concerns with 802.11. Again, we wouldn't be here if there weren't. And we do need a way to be able to test for security issues. And there are some tools that do exist. But what we really want is a way to be able to test for arbitrary security issues with our own custom tools. So what we need for that is we need a generic 802.11 toolkit. Going back to a previous point up there, newer, faster physical interfaces, such as A and so on, are being turned out on top of the same layer 2 protocols. That's important to note because as the 802.11 standard matures and you get these faster interfaces, people are still using the same layer 2 protocols with the same security issues. And I will go quickly through this as well. IEEE 802 LAN-MAN Standards Committee is where 802.11 was born. The WLAN, the Wireless Local Area Network Standard. Two physical interfaces are B and A. B is the one that we're all extremely familiar with, and we've got plenty of examples of it all around us here. Using the 2.4 gigahertz ISM band up to 11 megs, and then A is at 5 gigs at 54 megs. 802.11 was designed to be a drop-in replacement for Ethernet, such that all the upper layer protocols should absolutely be none the wiser of what's going on. And this seamless integration, and by large and way this does work, but it does come at a stiff price. There's a lot of complexity with the 802.11 protocol, and we will see that when we look at some of the headers, the different frame format, compare it with Ethernet. 802.11b is most widely deployed. It's the physical interface that is most widely used is based off of digital sequence sped spectrum. 2.4 gigahertz ISM, that's the unlicensed frequency that we talked about before, blah, 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 and certain limitations, scientific, medical. So you got your, your cell phones, your microwave, or rather your cordless phones, your microwaves, your baby monitors, and all that stuff. There's actually 14 different frequency divisions or channels, only 11 of which are sanctioned for use in the US. Okay, that's great. Let's sort of move on here to more protocol-oriented things. At the MAC layer, 802.11 is a carrier-sense multiple access collision avoidance protocol. That's how it accesses the medium. It's media access control. And that's the same as Ethernet type of, the CSMA. CSMA is a listen before talk protocol, exponential back off and retry. It also has a collision avoidance via this physical carrier sense where it listens to the wire, but also has sort of a logical virtual carrier sense with a network allocation vector, which is duration ID is the actual name of the field within the 802.11 header. And what this does is when you send out a frame that contains a duration ID, this informs all the other stations that receive this frame how long you're expecting to be using the medium for, and they should wait the nav. They should wait that much time. Two different ways to set up 802.11 networks. Ad hoc, which is peer-to-peer, which is you pop in a card, I pop in a card, and we don't need anything else to communicate. Or you have infrastructure mode, where you've got actually access points that connect you to a legacy wired network, such as what we've got here. Now let's talk about a sampling of some of the management frames that you'll see with 802.11. The beacon, which is transmitted frequently, which announces the availability and capabilities of the access point or the basic service set. This is, of course, only in infrastructure mode. Probe request and probe response, those are two frames. The probe request you generally see from client stations. And these are client-initiated requests for a wireless network. And the response, the probe response, is generally the same as a beacon. You have your associate request and response, and that's when you actually are telling the access point, I want to join the network there. I want to be a part of the basic service set. And then disassociate, which kicks you off the network. Some control frames. By the way, I probably should have mentioned before, there are three main types of 802.11 frames. There's management, control, and data. So some of these control frames that we see, there's the RTS frame, which is request to send. This is, you generally see the RTS, CTS protocol to either avoid the hidden node problem, which is when you've got access point, rather station A, station B, and the access point in the middle. Station A can see the access point, station B can see the access point. Station A cannot see station B. As such, they listen to the medium, they think it's quiet. He listens to the medium, thinks it's quiet. They both send at the same time and result in a collision. That's called the hidden node problem. RTS works by, I want to send a frame, I send out an RTS to the access point. The access point gets that, sends out a CTS. Since he can hear the access point, he receives a CTS, knows that there's going to be a transmission happening, and he will wait. This protocol also happens when there's a parameter in a lot of configuration utilities for 802.11 hardware for your RTS threshold. And it's usually a packet size. So if you have, say, a 1,000-byte packet or larger, then this protocol, this 4-byte sequence or what have you, or I'm sorry, 4-frame sequence will be initiated. So here's what we're looking at when we're talking about a generic 802.11 frame. A lot more complex than Ethernet. Those of you who are familiar with Ethernet, you've got a destination address, 6-byte destination MAC address, 6-byte source address, and then a 2-byte type, at least for the DICS Ethernet 2. The 802.3 Ethernet's a little bit more complicated, but who uses 802.3 anyway? So first you got your frame control. These are your control flags, and sort of talks about the version of the 802.11 that's currently being used. We'll look at that in a second. This is an overview. Duration ID is the nav that I talked about. Then you've got your three addresses, which are usually source, destination, and BSSID. Sequence control, and then address 4, which is used only when you have frames that are going from one distribution system to another distribution system. In other words, from one access point to another. Then you have optional data, and then your frame check sequence. So if we look at the control field, protocol version, which is, as we'll see in a minute, is always 0 at this point. Your frame type, control management or data. The frame subtype, which could be one of the many different management frames, subtypes, control frame subtypes, and so on, data frame subtypes. Then you have your control flags. 2DS is usually what a station sets when it's sending a frame to the distribution system, to the access point to be received by another station. from DS is coming from the access point. Fragmentation field, which you see that being set when you expect your wireless medium to be excessively noisy and you're worried about frame loss. Retry bit, power management, more data, WEP, other, and so on. This stuff is sort of ancillary to the, the main presentation, which we'll be getting to. But I made some nice pretty slides here, so I would like to talk about them a little bit. Protocol version at this, like I said before, is 0. Your management frame, control frame, those are the actual, if anyone really cares, those are the bit sequences to indicate those types of frames. Those are all the frames that are currently recognized, I believe, by the 802.11 standard. So we all know there's a lot of problems with 802.11, and a lot of corporations are making the buy no buy decision based upon these issues that exist. I'm not going to talk about WEP. I'll mention the issues with WEP, but that's been done to death. I will touch down on some of the issues with management control frames, such as probe requests and probe replies, the fact that there's no authentication or encryption, and some vendor. I won't talk specifically about specific vendors, but I will note the fact that vendor-specific issues, as with any traditional wired network security, or network piece of infrastructure, you're going to run into problems with vendor A's versus vendor B's because they're from different code bases. So this is no different here with 802.11 from some of the research and testing that we've done. Problems with state maintenance and fringe frames and packets. WEP stuff, WEP weaknesses. We've all heard about them, we've read about them, we've all run AirSnort and so on and so forth. Key sizes, weak IVs, growing the key space via induction, the so-called ARBA attack. ARBA, excuse me. Key management issues, which really aren't, addressed in the 802.11 standard. Some management weaknesses. Management frames and also control frames are neither authenticated nor encrypted. As such, even when WEP is turned on. As such, this is sort of, this is your so-called out-of-band control, and management channel. And since anyone can gain access to this in band with the rest of the medium, it's sort of a bad practice. As a security professional, I'm sure there's a lot of security consultants here in the audience, and as a matter of best practice, when you're setting up a network, a network infrastructure, you've got your IDS on one network over here. You want to have a back channel for the management network, so somebody can't gain access to that too easily. It's not in the hostile part of the network. Well, in this case, the management channel is within the hostile part of the network. Excuse me. Information leakage is obviously, or information disclosure is a big one here. I can enumerate clients as well as access points. This stuff should be all known to you. The net stumbler stuff. I can learn about, I can learn different things about your network from all this stuff. This is good information. The fact they're neither encrypted nor authenticated means I can spoof them pretty easily too. And denial of service becomes trivial. I'm sure we can, talk about radio-based denial of service attacks, but there's also protocol-based denial of service attacks that we can do. And I will be demonstrating something along those lines later, God willing that everything works out okay with the live demo. There's, like I said before, 3 different access points in here, all in a different channel. Association thievery, I can steal your association if I can knock you off the network. And data injection, These are all attacks we've seen before in traditional wired networks. These are all well documented. Of course, flooding, which again, is denial of service. Vendor-specific weaknesses. Every device is different and often from a separate code base, especially I imagine with the 802.11 stuff, since there was never really a standard code base to start with. You had a lot of your originally when a lot of wired infrastructure, you'd come up with vulnerabilities in even in operating systems. A lot of stuff was based off of, you had your BSD stacks, and you find 15 vendors vulnerable to the same vulnerability. In this case, you'll probably find some of that, but we've seen, a lot of different things. Different sizes of state tables, meaning that I can flood your access point, or possibly even your card with different types of packets with different amounts of data, different amounts of different amounts of traffic. Different sanity checks on packets and frames. If I send, maybe what might be illegal for an 802.1x frame, I send an illegal 802.1x frame. Maybe your check isn't quite fully implemented. 802.1x is extremely new. crashing is a big problem there. And of course, different devices with different types of management interfaces. SNMP, we all know how problematic that is, especially with all the ASN.1 vulnerabilities that were released. You know, if you share a code base with that, then you got to, you know, never mind the fact that you're probably running SNMP v1 with, you know, default community names, but now you've got a big problem with, you know, privilege escalation or otherwise. And then there's OpenFront Telnet, which seems to pop up everywhere these days, all sorts of different access points. And then also, which is not listed up here, is non-SSL based web management stuff. So that's pretty much all for the summary of the 802.11 primer and weaknesses. And bottom line is, it's a new protocol. These are problems we've seen before, and I think that, you know, we can all see they're exacerbated by the fact that a shared wireless medium is inherently insecure, as Bruce talked about earlier. There are a myriad of tools and toolkits around that exist to test for similar vulnerabilities on wired networks. There are several toolkits available, Libnet being one of them. Libnet allows you to build network security tools pretty easily. It allows you to build packets with a relatively abstracted interface, and also has packet injection primitives and things like that. There's Doug Song's libDNet, which is the so-called dumb networking library, which has a lot of really useful low-level network routines in a portable library, such as ARP lookup and route table lookup, an abstract interface for addressing, and he also contains some raw and link layer packet injection stuff as well, but it's more down and dirty. libpcap, which is the ubiquitous packet capturing and frame capturing library. Use all these things together and you can build some pretty cool tools. So some of the existing 802.11 network security tools. AeroPeak, which a lot of people are probably familiar with. It's a wireless frame sniffer and analysis platform. Really, really robust, really cool. Has a lot of, you've got your expert analysis stuff. You've got all sorts of different, pretty much everything you can imagine you can do with wireless traffic, you can do it with AeroPeak. But where AeroPeak's also very expensive, and it's obviously not open sourced. As sort of an aside, I actually live in the same town as a company, Wild Packets, that puts out this product, and their building burnt down last week or 2 weeks ago. So they're fighting the good fight though, and they're maintaining, and I guess they're a few miles away now. But if you haven't checked out AeroPeak, it's really cool software. Then there's open source AirTraf, which touts itself as sort of a pseudo IDS, wireless sniffer analysis platform again. This one is open source. AirSnort, which is the ubiquitous web key cracking utility, and NetStumbler, which is the access point enumeration tool. These tools, most of them are very task-oriented and specific of what they do. Closed source tools, obviously, they're not tunable. You couldn't take NetStumbler, which is closed source, and change it to say, well, okay, it sends out broadcast probe requests to get the probe responses back and uses that to enumerate access points or clients that are in peer mode. What if I want to make it listen for beacons? Well, you can't do that. So that's what tough luck Dorcas means. In order to test for unspecified security issues, we need sort of a generic testing framework. And that sort of moves us on into our case study here, the Byzantine generalist problem. It's important for an 802.11 network, obviously, to be robust. And according to Webster's, robust means strongly formed or connected. And Byzantine robustness means that your network is going to be proof against Byzantine failures. And a Byzantine failure is when a node on a network fails, not simply by ceasing to operate silently and sort of as a good little neighbor just going right down, but they misbehave in some way. That could be due to a misconfiguration, like in a router config, or malfunctioning hardware, or it could be a malicious individual in your network doing bad things. And this is actually taken from the Byzantine generalist problem, which is a computer science problem, which I've actually given this presentation before, and I was told to remove my discussion of the Byzantine generalist problem from it because it adds nothing to the presentation and it was confusing. So we can talk about it later if you're at all interested in it. The Omerta attack, if anyone's familiar with this presentation, they know that I like to do a live demonstration which demonstrates the utility of both the toolkit and also the need for arbitrary 802.11 custom security tools. And what this is sort of a virtual demo of is you've got your 802.11 network, much like the one in this room right here. You got your clients associated into the access point, and along comes your malicious interloper over here. Start sending out, Byzantine faults. In this case, these are spoofed disassociation frames. And Bruce touched down in the last presentation on this disassociation attack. We'll be covering in a little more detail here. So what happens is these associations go away. They get knocked off. There's no, again, management frames, neither encrypted nor authenticated. You're booted off right there. And the sad thing is there's nothing you can do about it. We actually sat on this for a long time before we ever talked about it publicly until it was actually released by other people. So we've actually talked to people who sit on the IEEE committees about fixing the 802.11 protocol. And I'm not exactly sure where they are on that. Clients are going to try and reassociate, but they're going to keep getting knocked off. It's pretty standard, pretty simple. All right. Byzantine fault injection. By the way, the tool name is Omerta, and that is the Sicilian code for silence. And it was also the handle of an esteemed guy once upon a time back in the computer security underworld. Theories are nice, but code is better. And we're going to go ahead and give it a try here and see how well this works. So I'm logging in over here. If there was actually any way to be able to put this on the other screen, I would have done that. I don't know if there is. Ray, was there any way to do that? This is going to be quick anyway. So as we'll see in a minute, I'm setting up the card here in the library to be ready to send frames. How many people know what channel they're associated in right now? As I was talking about before, okay, I know you're on 7. This guy's on 7. Does anyone else have any idea if they're on 7? There's 3 access points, I believe, in the convention area here, and they're on all separate channels. You're on 1? 6. 6 is, I think 6 is a rogue access point or something. I think they only set up 1, 3, 5, and 7. I don't know. Maybe it's fuzzing a little bit. So I'm setting on channel 7. I've got a 9 dB gain antenna over here. What this does is, let me run the attack first and see if we actually get anything working out of this demo here for us. So if you're actually on channel 7 right now, you're going to get booted off. Like this finding man over here probably is, but anyone else who's on a different channel will be unaffected. That's this tool is sitting here listening for data frames as they come in. It's turning around, it's swapping the addresses, it's spoofing a disassociation from the client up to the access point, killing all the state for the client's association on the access point. The access point no longer knows anything about your connection, therefore it ignores your data. Eventually, if the client figures this out, it will then try and reassociate. And depending on how effective this is, I've got a 9 dB gain antenna, omnidirectional antenna in here. If everyone was on the same channel, just about everyone would be knocked off. It works pretty well, especially in such an open area like this. However, we've got, I've already sent out about 600 frames just in the few minutes I've been talking here. So I've killed it. You probably are going to get, you should reassociate, no problem here in a minute or two. The other thing is since there's several access points in here, your card may opt to switch channels. So anyhow, in order to ferret out Byzantine failure vulnerabilities, such as this one, requires arbitrary security tools or toolkits to be able to build these tools. I can talk about stuff like this till I'm blue in the face, but until I can really demonstrate it and show you that the threat is real, lots of times people don't listen. A good example of this is the SYN flooding, fiasco of '96. If anyone remember that, there was, everyone knew about this problem for years and years and years, and no one looked at it. Nobody cared about it. In fact, Bellevin, I can't remember if they mentioned it in Repelling the Wily Hacker, but. Well, Morris 1 was also, exactly. So, but no one did anything about it until there was this widespread SYN flooding attacks across the internet. After that, people started working on code, the SYN cookie stuff, and increasing the what's the queue called? I can't remember. It's been so long. Anyway, that brought it to the forefront. Another thing that bears mentioning. Actually, we'll talk about this attack in a little more detail in a second. So a generic toolkit allows an application developer to build tools to test for Byzantine failures scenarios via I don't need to swap out anymore. But thank you, though. Some other guys were asking about it, so it's not all for naught. We could, by controlled Byzantine fault injection, we can find these vulnerabilities and possibly fix them before they become real issues, or at the very least, highlight them. Another example of such a toolkit for wired networks, of course, I always fall back on Libnet. It's sort of like a crutch of mine because it's I don't know, it just is. And we're actually going to be integrating Libradiate, which is the tool that was used, Toolkit used to build this tool with Libnet. So this is actually an arrow peak frame dump of a very similar attack, what we just went through over here. You see the beacons across, your access point setting up the beacons. As soon as the Byzantine fault injector sees the data, he starts spoofing disassociation frames. Out they go. The data is ACKed, but the client is then disassociated. Client doesn't know what's happened, tries to progress, tries to get back in, but as soon as more data goes, it's just dissociated again. Depending on how strong your card is and how strong the radio is and a lot of other parameters, this attack can completely remove you from the network until it's done, or you might be able to sneak a few frames in, get reassociated for a little while before you boot it off. It also depends on how many people are associated in this room. The firmware, as we will see, that this driver is built on top of, and the driver itself are a little bit shaky, and they don't do so well with a huge volume of receiving and sending, because the card can only do one at one time. It can't do both. So let's start talking about Libradiate. Libradiate is, I fall back to Libnet. It's the wireless analog. Is anyone here? Is anyone here familiar with Libnet at all? Is anyone here? How many people here are C programmers? All right. There's going to be a lot of code coming up here. I'll do my best to make it painless. So it's very early beta right now. It is publicly available. We did actually at the CanSec West conference back in April. We did release it. It is a 802.11 frame capturing, creation, and injection library. And what it does is it abstracts all these sort of onerous and tedious tasks into sort of a really simple portable interface for you. Not portable, rather, because it's tied to the hardware, as we'll see. It's a simple C library consisting of just a few function calls at this point and a single header file. Version 0.3, which is the version that is current right now, only runs on the Intersil Prism 2 based cards. These are your SMC cards and your D-Link cards. The one that I have in here is a modified SMC card to accept an external antenna, which you see here. I've heard reports that the Prism 2.5 chipset comes up with random errors. It doesn't work. I don't know for sure. Additionally, we would love to support the Cisco AeroNet cards. They're 100 milliwatts. I think they're actually 200 milliwatt cards are starting to come out now, but I don't feel very comfortable sitting on a laptop on my lap with a 200 milliwatt transmitter. But they're powerful cards. There's been some work to port this to the AeroNet cards, which would be great because, again, these are 30 milliwatt cards, these are 100 milliwatt cards. So first, we won't go into the code too quickly. We're going to start with pretty pictures at first. This is what it sort of looks like on a high level. I build my data frame, and I send it off to the access point. I build a management frame, and I send it off using Radiate. I think that's it for this cute animation. Okay, let's talk a little bit about the Radiate and the related component relationships. So at the most basic level, this is tied to the SSH.com host AP driver, which is sort of analogous to the WLAN NG drivers. The host AP driver has more support for doing raw frame injection and capturing, at least better support for the version that we're using here. This is tied directly to the Prism 2 firmware, which is, the driver is also tied to the Linux kernel. So that ties us to Linux 2.4.x kernel. We've got 2.4.7 here. On top of that, Radiate is built on top of the SSH.com host AP driver. Libnet, which is portable to other operating systems. We use that as sort of a peer to Radiate. And then we build our tools on top of that. The Omerta tool, which you just saw, was built solely on top of Libradiate. The Disperse tool, which we'll look at next, which we actually look at the code for, is built on top of both of these. So let's get a little bit more detail here. We start off, we call Radiate init. That initializes the library. The library is then initialized. we call the function radiate build management frame. That builds our management frame. We write the frame out, and that writes it to the ether, to the air. We then shut down the library, kill all the state, and that's how simple it is, basically. Of course, there's arguments that go in the middle of there. You got to put a bunch of stuff in the middle, but that's basically how simple it is. Okay, this is the point where all you non-programmers, I'm not going to get offended if you guys get up and walk out, but I will take questions at the end. This is my cute little introduction to the code that's going to happen here. You don't have to take notes on this or read this or anything. It's just eye candy. It's just pretty. So first, we'll start off by talking about the Radiate context. This is your state holder. This is where you maintain the state when you initialize a Radiate session, and the framework functions around that. At this point, the Radiate context is really simple. It contains a file descriptor, a byte for your control flags, and then an error buffer. Radiate init is your initialization function. That's when we call that, we've actually started up the library. Destroy will actually shut down the state and the session for you. So at this point, we're only building management and data frames. We don't have any control frame building functionality yet, just because I've been too busy to add it, and it's a little bit different since control frames are shaped a little differently. But anyway, you pass in your char pointers to the addresses, and these are your 6-byte MAC addresses. Again, source, destination, BSSID. Your subtype, which is the subtype of the type of frame in question. For your management frames, this could be association request, association response, disassociate, beacon, what have you. Your control flags, WEP, to DS, from DS, power save, things of that nature. An optional payload. So if you wanted to include your payload directly after your management frame, you can do it that way. And then if you actually include a payload, you tell it how big the payload is. Finally, you include your context variable there. Same thing for a data frame, exactly the same prototype for the function. The only difference is happens underneath. So over here, is this all legible anywhere, either in your book or on the screens? Okay, good. Here is actually what the management frame subtypes look like. This is sort of exactly what we looked at before with the bit codes. Management subtypes, data subtypes, and control subtypes. So if you wanted to specify a disassociation frame, you pick the third from the bottom in your subtype, and if you wanted to turn on the WEP bit for some unknown reason, I don't know why, but if you did, you pick the second from the bottom there. Capture and injection functions. Radiate read is what you would use to actually read from the ether, and you pass it into a pointer to a pointer which will contain your data. The function, I suppose we've been talking about return values. All the functions return 1 on success or -1 on error. Again, you pass in your context. Radiate write, you pass it, it's real simple, pass that pointer to the completed build frame as returned from one of the build functions. You pass in the size of the frame and then your context, and that's it. As a matter of note, the HFA384X primitive that you see up there, that's actually tied to the firmware. That's what the frame looks like when you read in a frame from this firmware. This is what you would, if you're a programmer, you could cast it into this and pull out some additional information. Above the 802.11 header, there's sort of frame statistics and things like that. Radiate set monitor mode and radiate get error. These are just some, by the way, this is it for the functions. It's a small library. Set monitor mode allows you to, one thing I should have mentioned earlier actually was the fact that when you put a 802.11 wireless card into what's called monitor mode, it sort of tells the card to stop processing the frames as it would normally and sort of act as much as it possibly can as a passive radio. Monitor mode 1 does this. This is a function, this is actually sort of a wrapper to an IOCTL, it's input-output control function that allows you to dip right into the kernel, turn this monitor mode on or off. As I said before, this driver is a little bit flaky when you're trying to cram a bunch of frames through it. So what I've found is successful is turning monitor mode on and off, flipping it on and off, going back and forth. So as such, we've exported a function to be able to do that. And actually, in some of the code that I've written, you put that, if you're doing if you're looping on packet capturing and packet injection, you put the setting the monitor mode back and forth there, and that seems to work a lot better than if you didn't. Get error allows you to pull, say a function return -1 for some reason, -1, there was an error. Radiate get error will allow you to pull out the error message from the Radiate context itself. The whole point of having this Radiate _t as a context variable is sort of to facilitate interface hiding. So you don't need to know what's going on under the hood. You just need to know that it's going on. And if you need to get additional information, we have functions to pull that out for you, such as Radiate get error. The alternative would be to have it just be a non-opaque structure where you could pull the error yourself. This is just a little bit more abstract. So let's look at this more in practice now. We're going to initialize Radiate. Again, we're going to get a context. The communication with the kernel happens via a netlink socket. And the context, as I said before, maintains state. And that's about it. That's how difficult it is to initialize the library there. You just call Radiate _init with the control flags. At this point, there's one flag for verbosity, for error message specification. So if you want the library to tell you every time something bad happens to the standard error, to your terminal, you can do that. In the future, we'll probably support more flags. And that's passing an error buff also, because if there's a problem with the initialization, you're not going to have a context with which to pull an error message from, so that's why you need to pass in your error buffer sort of as another argument there. If this function returns null, then there was a problem with the initialization, and hopefully it was something fixable. Data frame creation. This is basically what it looks like when you're building a data frame. You've got a uchar pointer, which is effectively a byte pointer. You have a pointer to your data, which in this case is just going to be sort of a string. Excuse me. You pass in your addresses, your source address, your destination address, your BSSID, which is again the address of the access point. Passing in the Radiate data subtype, because you're just sending a regular data frame. We're not going to specify any control flags. There's our data. Our data is of size, whatever, how long that string is, and we pass in our context. If this buffer returns null, then there was a problem building the frame, and we pull the error message out as per Radiate get error. Otherwise, we've got our frame set up and ready to go. Same thing for management frame creation. In this case, we wanted to send out a disassociation frame. Our data this time is actually going to be data frames, or rather management disassociation frames. Their data is always going to be the reason code for why you're being disassociated. In this case, your previous authentication is not valid. To capture a frame, again, we have a buffer, we have a counter. We call Radiate _read with the address of that buffer and the context. If we read no bytes, -1 rather, -1 indicates that there was an error in reading, otherwise C will contain the number of bytes read. What are we doing on time here, by the way? Spectacular. We're in the home stretch here, so I'm going to start talking a lot slower. No, we'll probably be out of here a little bit early, get you guys to lunch a little bit early. Except for those guys leaving right now. If I had the spotlight, I'd shine it now. Frame injection is summarily also very simple. You call Radiate _write with the frame size, and your context. Returned are the number of bytes written or -1 on error. This is all pretty standard stuff here. So dipping out of the code real quick, we look at the OSI model. Radiate builds your layer 2 stuff, obviously. We use Libnet to build a layer 3 and above headers, and then we can build some pretty cool stuff. Any programs that you wanted to build in a wired network that would use Libnet or something along those lines, or your other favorite packet creation and injection library, you can do that with now using Radiate on a wireless network. As an example, the RBA inductive attack was implemented using Libradiate and Libnet. Both those should be in there. Remember, theories are nice, code is better. Up until RBA for those of you familiar with the Arbor attack, this is the one where you would grow the WEP key space via induction. It's a known plain text attack against WEP. And it was all theoretical until we actually implemented it in practice. So this is what the disperse tool that we're going to look at now, this is what we're going to end up building. Is this legible at all in the book? That probably isn't, is it? Because that's some animation on top of it. Well, first you've got your 802.11 header. That should say 802.11, not 802.11b. Then you've got your snap header next, which is your subnetwork attachment point, which is not something I'm going to go into. It's an IEEE hack. Then you've got your IP header next, and then you've got your ICMP header. This is what your frame is going to look like. Radiate's going to build the first half. Libnet's going to build the second half. And this is how complex it gets in real life. So using these two guys together, we're going to build a small program called Disperse. And Disperse allows you to send out an ICMP echo packet using 802.11 as its link layer protocol. Small program, 300 line with a lot of comments. By the way, this is also distributed with the 0.3 version of Radiate, which you can get from the website, which I will give at the end. So only the stuff in red is the stuff we're concerned about here. And as people seem to be dropping like flies for the programming stuff, I'm going to go through this somewhat quickly. If you guys want me to slow down or point anything out, feel free to ask. I'd love to answer a programming question. Hopefully I can. Okay, the first thing that we look at up there is the LLC, the link layer control snap header. Again, as I said, it's sort of a hack. It's a hack to be able to use non-IEEE protocols with IEEE-based link layer stuff. I'm sorry, non-IEEE network layer stuff with IEEE link layer stuff. Then we have our control pack structure for Disperse. Inside there we have our Radiate context. We also have our Libnet context. Then we have a bunch of bytes, one for the protocol, which is not used because this program is only sending out ICMP echo packets. At one point I was going to rewrite this program to send out arbitrary packets, but I didn't have time to do it, so it just does one type. Then you have your pointer to the actual frame, which is going to be sent out. Your destination MAC address, your source MAC address, your BSSID. All these are things we've seen before. Your 4 bytes for your destination address, IP address, your 4 bytes for your source IP address, and then a pointer to payload. So the main thing to look at down here, by the way, this program is complete as per pulled from the actual .c file. The stuff in red is the stuff we're concerned about. First thing we're going to do is we initialize a Libnet. Libnet initialization is much the same as Radiate initialization. We're just initializing it using the IP4 raw interface. And we're actually not going to use Libnet's packet injection stuff. So it's more of a dummy context just to be able to use Libnet's packet creation features to build our IP header and our ICMP header. We don't care about the network interface. That's why the next argument is null. And then again, we pass in an error buffer in case there's a problem with initialization. You may notice that there's ADV for advanced that initializes a library exporting a few extra functions to be able to do some advanced functions that we'll see later on here. The next thing we do is there's some handy functions also within Libnet to allow you to read from the command line arguments and sort of put them in the hexadecimal Ethernet addresses and put them into a byte array for you. And that's what this function does, hex ASCII to numeric. And it reads from the command line and stores it in, first you get the BSSID. So at the top of that switch statement there, we see case B, and then the libnet under hex under A to N. So whenever the user specifies -B at the command line and passes in a 6-byte MAC address, it's going to be stored inside the BSSID pointer. Same with the destination address, same with the source address. Then down here, we do some sanity checking on the arguments. Finally, we get down where we initialize the Radiate context. No, we're not specifying any of the flags, so the flags byte is null, again with the error buffer, just in case anything bad happens. First thing we do is, the way that I like to build packets and frames and all this good stuff is I've sort of changed the model. I build them like an operating system kernel, so I'm going to start at the higher levels, at your application level, at your transport level, at your whatever. The highest we got here is well, technically ICMP is sort of like your transport right now because that's sitting on top of IP. So we start with ICMP. That's how your OS is going to build it, right? You go down the stack from higher to lower. So we call Libnet build under ICMP v4 echo. We're building a IP version 4 echo header. Specify all the arguments there. I'm not going to go into too much detail. You see that we pass in the context there at the end. The p tag is just a way of maintaining sort of a pseudo pointer to the header that we've just built in case we needed to go back and modify it later, which we're not going to do. Same thing for IPv4. We pass in the total IPv length there, IP header length rather, which if anyone cares will be 28 bytes. Then we make sure Libnet under toggle checksum. We make sure that it will compute the checksum. Here's some sort of trivia for you. Raw sockets interface, which is what we would be using here. Whenever you build and send a packet using the raw sockets interface on any Unix operating system anywhere, I've yet to see anything different. The kernel will always compute the checksum for you. So as such, if you want to save time when you're using this interface, you don't compute the checksum, you leave it 0. The kernel will compute it for you and pop it in there. Libnet takes advantage of this and doesn't compute a checksum when you initialize it using the raw interface. But I wanted to compute the checksum here because I'm not actually going to use the kernel's interface to send the packet out. I'm going to use Radiate. So I tell it, hey, guess what? You need to compute the checksum for me. Here's where the advanced interface comes into play here. Normally, we would build this packet, build the ICMP header, build the IP header, then call a libnet write function, which is real simple, and it will write the packet out to the network, or the wired interface, whatever. But I don't want that to happen. I just wanted to use Libnet to build a packet for me. So I call this advanced function, which will go ahead and inside of Libnet's buffer management system, it will pull the packet pieces out, put them together for me in a contiguous buffer, compute all the checksums, make the packet wire ready and ready to go. And that's what call packet does. Libnet advanced for the advanced interface, call packet. Pulls it from Libnet's internal state machine, basically. Then the next thing of interest is, again, remember we start at the higher levels and work our way down. We're starting, technically ICMP is sort of adjunct to IP, but I think of it as a transport. So pseudo layer 3, layer 4, then down to layer 3 IP, and then we're down to layer 2, which is where the Radiate stuff comes into play. Building a data frame, passing the BSS ID, the MAC address for the source, the destination. Remember, our subtype is just regular data. We're sending it to a distribution system. We're sending it to the access point. If we actually compiled this, ran it, and everything, we could, ping a host on the on the wireless or on the infrastructure side of the network. Passing our context. Payload in this case is our ICMP header that we just built, and then we just write the frame out. And we're passing in the entire size of the frame, which is the size of the ICMP header, which is the size of the entire frame, plus the snap header, which is another 8 bytes. And that's about it. Down there you see the do_IOCTL. That is just a wrapper to the Radiate set monitor mode function that I talked about before to sort of reset the card. It sets the monitor mode back to 0, which is regular mode, back to 1, which is sort of like do what I tell you, act as a passive radio mode, and then we're done. And that's about how complicated it is. Depending on how comfortable you are with your C programming, this is either simple or complicated. Before you can actually just go ahead and start using the library, most of the coding stuff's done, by the way, so we're out of the woods there. Obviously, you have to make sure the library is built and installed properly. That's not very hard to do, though. You want to pop the Prism 2 card in, and you wait for the delightful doot-deet, the little beeping sound that Linux always makes when you have the PCMCA drivers. Anyone who's wrestled with the PC card stuff, the drivers under Linux, knows that that's just, it's a very soothing sound to hear it go properly, and when you hear that low tone, it sucks. That's no good. So if you don't hear the brightly colored tone, there's probably a driver or PCMCA issue, but you're very smart, so you won't have any problem figuring that out. You put the card into monitor mode, as I've talked about. Monitor mode makes the card act as a passive radio, more or less, at least technically it's supposed to. It's supposed to be able to read frames without processing them, and it also takes stuff sort of without processing them. We set our channel, which is why I was having issues earlier with this demonstration, the Omerta attack, because I have to tell the card what channel to be on. I could alternately, export that to another interface and have it change channels as it goes through, but it's sort of a proof of concept tool, and we don't, it doesn't have to be that powerful. And then we run it, and that's that. The Radiate's available from packetfactory.net as per the URL that's up there. Disperse is included also. The Omerta stuff is not really for distribution. It's more of a proof of concept. And I do get a lot of people asking me, what's the point of that? Great, it's a done service tool, congratulations. And like I said before, first of all, it points out the problem. I can talk a lot. It's a lot better if I can just do this and show you. Second of all, the utility of denial of service attacks is limited, except when you combine them with other more sophisticated attacks. If you consider where if I was able to target any one of you and kick you off the network and steal your association, that's a little more compelling. I can target any one of you, kick you off the network, let you reassociate. Perhaps there's information I can glean from you while you you negotiate your 802.1x credentials, things like that, or whatever else may be going on. Perhaps there's state information I can get. Maybe I can watch you do this many times and get a lot of information out of that. Denial of service attacks generally can be the building blocks of other more complicated and sophisticated attacks that need attention and require people to know what's going on. So right here I have a 9 dB gain Omni, which spreads the signals out in basically I think a 360 degree radius. Or we have the directional, which I think is about a 15 or 30 degree directional signal, which you can set up from I forget, anyone at 13 dB, about 5 miles, something like that, several miles. You could sit there and do all sorts of fun stuff with it. You put it on a tripod there because you want to make sure you can aim it very accurately. Some of the issues that we know about here, we are at the mercy of the firmware. And as I've mentioned a few times throughout this presentation, is that the driver and the firmware itself don't always do what we want them to do. One call to write will often result in several frames, and I'm not exactly sure why this is. Sometimes you'll see eight frames being written for one, at least with management traffic. Problems with sending certain frames in order to set the 2DS bit, in other words, to send a frame to the distribution system, requires that you recompile the kernel module with that primitive that you see there, that macro defined. And what that does is it changes how monitor mode works, but then you can't sniff frames. It's sort of a catch-22, I guess. It would be nice if we could actually have the card act as a completely passive radio and do exactly what we tell it. You sniff when I tell you to sniff, you write exactly what I tell you, and don't give me a lip about that. The driver tends to crash or fail miserably when the card is removed and reseated frequently, so that's another issue, which would be another nice reason why if we could port to the the 350s, the Cisco cards. The features of Radiate, it is somewhat rough at this point, but it does work. There will be code cleanup. There might be interface changes, so don't write your enterprise-wide applications on top of this, although I don't think anyone's going to be doing that. Perhaps there will be buffer management. With pblocks is how Libnet does its buffer management. A possible API change to accommodate different layer 1 interfaces. That will probably happen if we start supporting other cards, because the HFA 384 FX header that I showed you before will change with different cards. And we want to support different cards. Perhaps we'll build this into Libnet, and then I won't always have to talk about them being separate. So to sort of close things out here, I'm going to do it on time, by the way. 20 minutes? Half hour? I'm supposed to be done at noon. That's right, it's only 11:30. Okay. Well, I guess I can sort of stretch this last slide out for a while. We need is a way to be developed arbitrary tools to be able to test for 802.11 networks for anomalous events. Byzantine failure was used as an example here. Radiate is a toolkit that allows the application programmer to develop tools to test for 802.11 security issues. I would like to give props and a good big shout out to Timothy Newsham, who was not able to make it to this conference, but he did a lot of the early work on this library. And pretty much everywhere I go, I have to sing praises of Tim Newsham, because if you're not familiar with his work, he's absolutely incredibly gifted, talented, bright guy. And he's a nice guy too. Smart dresser. I think. Oh, wait. Let me just close out here. I got like 2 slides left. As I mentioned before, Radiate is sort of like a component. This is not meant to be a book plug in any way, shape, or form, but just to mention it. I did write a book for Wiley called Building Open Source Network Security Tools, and I do define a paradigm for defining a network security tool. And Radiate fits into this model at the component layer, which is the most fundamental layer. You take these components such as Libradiate, Libnet, libpcap, libdnet, OpenSSL, what have you. These are different C libraries that you use to do different security-related things. You use those to build different techniques. A technique might be port scanning, a technique is packet sniffing, a technique is IP expiry, a technique is encryption, and so on. You combine these techniques to build your network security tools. Anyway, I'm not going to go on about this. If you're interested in it, you can email me. It'll be out October. So that's where we're at. We've got about 28 minutes here for questions. Yes?
What's the Byzantine general's problem?
The Byzantine general's problem? All right. Byzantine general's problem, since we have the time, is briefly classical computer science. Has anyone ever heard the Byzantine general's problem that's classically trained in computer science? A few people? Okay. I'm not classically trained in computer science. I've taken a few night classes at the community college now. Anyway, Byzantine general's problem is we imagine that there are divisions of the Byzantine army camped out around an enemy city, and these divisions are led by generals, and the generals observe the enemy for a while and decide on how they're going to attack, when they're going to attack, and what have you. They also then they need to converge on a plan. They all need to come to the same plan on how they're going to attack, and they need to communicate this plan to each other. The problem is that some of these generals may be traitorous and may report false information or not at all, preventing the plan from reaching convergence. And I think the formula works out to be 3t plus 1, that there needs to be that many 3t plus 1, where the t is the number of traitors, of non-traitorous generals before the plan can reach, you can guarantee to reach convergence, something like that. It's really ancillary, so that's why I pulled it out. I had people, because then the very next slide was the actual animation with the Omerta, with the laptops. There were 3 of them, and then people were starting to, well, 3t plus 1, where's the plus 1? Is that the attacker? And it has nothing to do with it, so, at all. Yes?
Okay, yeah, with Omerta, you're working with that rate, so WEP doesn't have any.
No.
But there might be an interaction with WEP. This is what I was curious about. When your WEP relies on the initialization vector, so if you disassociate somebody, you see initialization vector can reset back to 0, like entering the zone, initialization vector gets reset. You know anything about that?
I haven't done too much practice, too much research with the actual attack, with looking into WEP, because WEP is fundamentally broken to begin with, and there's already plenty of attacks where you sniff out the IVs, look for the weak IVs, and things like that. So we haven't really gone too deeply into that stuff.
Hey, Libradiate, how feasible is it to take a packet sniffed, modify it slightly, and retransmit it?
Depends on the packet type and what some of the bits are, but it really. What was that? Oh, I'm sorry. The question was, how feasible is it to take a sniffed frame? By the way, I'm sort of anal about how anything at layer 2 and below is a frame, or rather at layer 2 is a frame, anything layer 3 is a packet. So to take a frame sniffed, modify a few values, maybe some addresses, things like that, and write it right back out. Using the interface, trivial. Whether or not the firmware wants to let you do it, well, that's another story. Like I said, frames with the 2 DS-bit set, we were having some trouble sending those properly.
But max spoofing isn't an issue?
Not at all. Not at all. Arbitrary, set your address to whatever you want. Well, I'm sorry, go ahead.
Do the base stations have an independent address lower than the MAC?
Do the base stations have an address lower than?
Can you spoof messages from a base station?
Sure. Absolutely. I mean, the base station, the BSS ID is just a MAC address. In fact, the first 3 bytes of the OUI code are always going to be, that's how NetStumbler does a lot of its, tells you what the manufacturer of the hardware is, because it pulls up the OUI code, which is the first 3 bytes of any MAC address, the first 24 bits. Yeah?
I'm relieved all your fire alarms aren't going off.
Were you there?
I was there.
Okay, well, the DEF CON 3, or I'm sorry, Black Hat 3, the last time I spoke at Black Hat, it was at the Venetian when it just opened, and it was raining, freak storms in Vegas, and the fire alarms were going off the whole time. And I still haven't seen that presentation, but I guess I just sort of sat there for a while or something.
We're getting really pissed off.
Yeah, they kept going off, and it was in the middle of the presentation. It sucked. So, anybody else about anything? Yes?
In your application, you mainly stay in monitor mode, read data, and then switch out of monitor.
Yes. You can actually, yeah, the question is, do you stay in monitor mode while in the application? Yeah, I mainly stay in monitor mode, but like I said, I was noticing more successful results when you flip back and forth. It just seemed, the card just seems to like it better, and it took a lot of trial and error to get there.
And the 2DS, could you just elaborate on that again?
2DS is the bit that you set to distribution system.
Okay.
Yeah. You want me to elaborate on that more?
Well, you're saying there's a problem with that?
The card doesn't seem to want to send frames with that 2DS bit set when it's in that particular, when it's compiled without that macro that is specified. This is all in the documentation for the library also.
So if you compile with that, you can go from monitor.
Yes. Yes. Yeah. There's another question over here anywhere? Oh yeah, what's up?
Yes, is the Linux kernel stack not used when you use wireless on a cloud?
The netlink. It uses the netlink stuff, and that's about it.
So there's no way you can flip that set kernel on a traffic over a wireless connection like Radiate?
Not at this point. But if I plug Radiate into Libnet, it'll do it seamlessly. You won't know the difference, except.
How about on Windows?
What's that? Windows?
I have a wireless station and I can actually use Query on Windows to actually sniff my traffic.
Uh-huh.
So I'm really curious if I can use Libnet on that also.
Libnet is portable to Cygwin, so yes, Libnet is portable to Windows if you have Cygwin installed and all the development tools and stuff. If anyone have any more questions, just shout them out if you do, in the front.
Are there any particularly interesting things you can do with 802.11 that don't exist in a pure Ethernet?
Anything interesting you can do with 802.11 that don't exist?
Like for example, I know that you can bounce off the base station to get to another host that you can't reach directly. Are there any other capabilities of that?
I'm sorry, I don't still understand your question.
Like, there's a shit ton of complexity in 802.11.
Yeah.
What new stuff can we do with it?
Oh, well, you're asking for like zero-day stuff and all that.
Well, I mean, now that we have it directed, lined to it, we aren't tied to whatever the driver implementations want. Do you have any ideas of what we can do?
Well, that's kind of why the library is built, right? It's kind of up to you to sort of tinker around and find out. Some of the stuff that we have discovered, we can't really talk about simply because we've, some of it's vendor specific and come out of work that we've done. So a lot of the work that I do is within the At Stakes Wireless Center of Excellence, and that's sort of our virtual areas of domain expertise, and we actually do work for customers in this area. So some of that stuff is a little bit, like the disassociation stuff, we had that back in like January, but we couldn't talk about it for a long time, in December. Anybody? Yo.
Well, it's kind of related or unrelated, but to disclosure, if you're under contract and you're doing research, that information belongs to your contractor too. But some of the things, what is At Stakes policy on disclosure?
I'm not going to get involved in the religious debate of full disclosure, not full disclosure. I can't. The question was, what is At Stakes policy on disclosure? That is a religious argument that I'm not really gonna step into. I'm sorry. You can email Chris Wysopal, and I'm sure he would love to talk about it. But I'm staying away from that one. As far as the stuff here, the library itself was developed in At Stakes Center of Excellence and released with an open source BSD license, so that's free. Any of the proprietary research that we would happen to do in the Center of Excellence that was for a customer that we want you to evaluate the security of X or Y, that's theirs. If I write any code, that's theirs. I don't release that. So stuff like that. If I found a vulnerability, that's, again, we talk to them. And if we're going to do a release above beyond that, that's sort of where the religious debate comes in. Anybody? Yes?
If you did go for Libnet integration at some point, would you target the current stable release or the new one you're working on?
The new 1.1 stuff is going to be all that's supported. I'm like this close to going GA with it and making it It's pretty stable. It's got much more functionality. It works better. I can't think of any reason to use the 1.0 interface except that a lot of people have been using it. The advanced stuff that you saw, that I initialized Libnet with the advanced interface, that allows you a lot of the fallback functionality where the code's not portable, but the functionality is the same. You can build a packet, pull it out, and you'll have your packet right here in front of you. What Libnet traditionally does, the new Libnet, is it abstracts everything from the programmer such that you don't have to worry about managing buffers or anything like that. The P blocks are sort of like naive M-buffs, for those of you that know. The advanced interface, however, sort of obviates some of the state machine, and the control logic within Libnet allows you to get in there, get under the hood there. You can actually, if you wanted to just build your own frame yourself and write it. In other words, sniff a frame using PCAP, pull it out, swap the addresses, do a few changes here and there. You want to do it super fast. Libnet's been initialized previously with the advanced interface. You can call an advanced function to write that right out. You don't have to go through the whole buffer management process, the coalescing and all that stuff, which is somewhat slow. So 1.1 is going to be all that's supported soon.
Thanks.
No problem. Okay. If anyone wants, I've got a stack of business cards up here. If you want to email me or talk later or anything like that, feel free to approach me. And I actually got pretty close to the time there. And thank you for staying. And thanks a lot.